Okay guys, today we'll be doing, this is October November 2024 paper 22, and yeah, this is the paper which like recently came, and we'll try to solve it and we'll see how it goes. It says a sphere falls vertically through a liquid that has a density of 830 kg meter cube. The sphere has a radius r and a constant velocity. Constant velocity, this means that it is in equilibrium. Okay, we'll read more. Okay, so it shows us the object. A liquid is falling downward, and we know it is falling downward, and since it is falling downward, that it's falling downward due to its weight, meaning the upward acting force is the upthrust. We'll read further. The drag force acting on it, the sphere, is given by the formula. Determine the SI units of n. Okay, we'll do that. So we know d is equals to 6 pi into radius into n into velocity. We'll cut 6 and pi because these are dimensionless constant, meaning they have no SI unit, and we'll rearrange to give d upon radius into velocity. Drag force is a type of force, and force is, if you look at, and force is kg ms minus 2. If you want to see how you get that, is you should know this at this point, but it's F is equals to ma, m is equals to kg, acceleration is ms minus cube, so it's pretty simple. R is the radius, and we'll have that in meters, so kg ms minus 2, and we'll have velocity ms minus 1. So we'll do this, we'll simplify it furthermore. Kg ms minus 2 into m square s minus 1. So the m and m will cancel out, and we'll only have one m in the denominator, and minus 2 minus bracket minus 1 minus 2 plus 1 is equals to minus 1, sign of the bigger number. So it will get in the end kg, and because it is downward right now and it is 1, once it will go upward it will become minus 1, kg m minus 1 s minus 1. Okay, it's saying state an equation for the relationship between the magnitude of the weight, drag force, and upthrust acting on the sphere. Since we know it's in equilibrium, the sum of upward force will equal the sum of downward forces, and since it is an object, its weight is acting downward, meaning the upward acting force, which is the drag force, and the upthrust. So downward force is equal to sum of upward force. So you could say that the downward force is equal to the upward force. The downward force is W, is the weight, and since they are only asking in terms of WD and U, it's equal to the sum of downward force is equal to sum of upward, which is the drag force plus the upthrust. Then it's saying that the volume of the sphere is 4.6 centimeter cube. Okay, and the drag force we know. Calculate the weight of the sphere. So we already knew the formula, where is d plus 4 upthrust. Now upthrust, and this is very careful, a lot of people make mistakes, it's in centimeter cube. Usually when we calculate upthrust is rho vg. We have volume, we are trying to calculate the volumes in terms of meter cube. So a lot of people make this mistakes when calculating the volume. It's because it is saying that it's in centimeter cube. We know from centimeter to meter there is a jump of 100. You divide the value by 100 to get to a meter. If you have a centimeter, you want to go to meter, you divide it by 100. Hence 10 to the power minus 2. Basically minus 2 means that you're dividing it by 100 in a short term. If you're going from like a centimeter cube, so just 10 to the power minus 2 into 3, and minus 2 into 3, that will give you minus 6. So centimeter cube is basically 10 to the power minus 6. So we'll make sure that we're not making this mistake. So upthrust is equals to rho. We already know rho. It told us that's 830. So 830 into, what was the volume? 4.6. 4.6 10 to the power minus 6, and again 9.81. Let me just do a calculator. That's 830 into 4.6, 10 to the power minus 6, and then further multiply that by 9.81. 9.81. Alright, so we're getting 0.032. We know this value, and we'll add the 0.32 from our previous value, which is due to drag force. You might ask, where did I get this formula? Well, they told us. So I'm getting, my weight is 0.357, because the values of the question is given to us in two significant figure, and this is two significant figure, and this is two significant figure. We'll round this off to two significant figures, so we'll get 0.36. Okay, moving on to question number 2. It says define momentum. You could just say that it is the product of mass and velocity. Okay, what does it say? Child stands on a scooter on a horizontal ground. The combined mass of the पता नहीं क्या हो रहा है यार गले को मैंने, probably मैं नीचे बैठा हूँ इस वजह से हो सकता है. Okay, so भाई क्या कह रहा है? This is saying a child stands on a scooter on a horizontal ground. The combined mass of the child and the scooter is 16 kilograms. The child starts from rest and the child starts from rest, so we know that its initial velocity is 0, and pushes once onto the ground with her foot, which causes her to accelerate. The push lasts for 1.1 second, and the speed of the child after the push is this. Calculate the average resultant force. So this is very straightforward. Basically, you know the initial velocity, you need the final velocity, which is 0.60. Now they're asking, so we asking to know the resultant force. We know F is equals to ma. It's better if you don't use this example. You can very well use the example of like F is equals to delta P momentum upon time. I would much recommend that you write this delta P. So we know that M, which is 16 kilograms, and delta V is basically M into change in velocity. So change in velocity is just the final velocity, 0.60, minus the initial velocity is just nothing, divided by 1.1. I'll plug that into the calculator. I'm getting 8.7, and since majority of the data that we have been provided is in two significant figure, we'll also write this in two significant figure. This is two significant figure, this is two significant figure, two significant. It's rest, but okay. It says later the child travels down a slope at a constant angle to the horizontal. Okay, as shown. At point A, her speed is 0.6 meter per second and has a constant acceleration. Constant acceleration means that we can use the formula of kinematics. If you remember the formulas, u plus at, s is equals to ut plus half at square, and s is equal to sa is equals to v square minus u square. These formula will only be, you can only use these formulas when our acceleration is either uniform or constant. That's the only requirement. Okay, what it says later on, she has a constant acceleration of 0.58 second parallel to the slope. At time 3.7 seconds she reaches B. Calculate the distance x traveled by. Okay, so they want us to travel this distance. We'll see what data that we have. We have acceleration, which is given to us as 0.85 meter per second square. You don't need to write meter per second square all the time. I'm not gonna write it, it's tedious. At point A, so our initial velocity is 0.60. Okay, she has a time of 3.7 seconds. Do we know our final velocity? No, we do not. We need to find s or x in this matter, but we need to find the distance. So yes, we can find it out. S is equals to ut plus half at square. Some of you might ask, well, why didn't we use this formula? Because we don't know the final velocity. If we knew that, we could easily use this formula, but no need to do that, no need to go all that hassle. So S is just going to be 0.60 into T, which is 3.7, plus 0.85 into, I'll put a bigger bracket here, sorry, 3.7 square upon 2, 12.79. Okay, let's see how many significant figures should I round this off to. So this is 2 significant figure, this is 2 significant figure, and this is 2 significant figure. So I'll probably round this off to like 13. It's 12, sorry, it's 12.79. I'll round it off to 13. So I'll round this off to 13. Okay. Part D, it says at point B, the child in C applies a brake with a constant force to maintain a constant velocity. Point C is 18 meter from point B. Okay. Yes, it is 18 meter. The distance covered. So we know that the work done is just the force applied in the direction of the distance covered, and we are applying a force. So we know that this is 250, the work done, and 18. This is F. So we are getting 18.5, 13.8. And since majority of the data that has been provided to us in 2 significant figure, I'll round this off to 14. Okay, moving to part 3. It says that the variation of the stress and strain of a metal is shown. Alright, and point E is the elastic limit, and use figure 3.1 to determine the Young modulus. So we know that Young modulus itself is stress upon strain. Stress upon strain. So what you need to show here is that the gradient of this, actually, that is the Young's modulus. The stress, so there has already been marked. This is very important, that for point E is the elastic limit. So for Young modulus, you will not be actually required to use point E, because if you remember, point E is the elastic limit, meaning when a force is applied, it will extend, and when a force is removed, it will return back to its original position. But at elastic limit, the Hooke's law is not followed. Hooke's law is followed till the limit of proportionality, where the force applied is directly proportional to the extension observed. So this is the limit of proportionality. Limit of proportionality. And you'll use this to find the Young modulus. So if you look at there, it's just very simple. You need to find the gradient. It's here, and it's here. Okay, so stress, we'll write stress. What do we have as the stress? So it's about 10, 20, and this is, I'm assuming that that's 25, so that's 24. So this is 24, but be important, there's a unit written here. That's not just 24 watt, that's 24 10 to the power 7. That's 24 10 to the power 7. And as for strain, the strain is given to us in percentage. Percentage isn't a very big deal. Percentage just mean that a value, anything, it could be n, it could be x, or any numerical value has been multiplied by 100. So if it says it's 1% here, you will take 1 and divide by 100, which is, I think so, is 0.01. So you just divide this by, okay, you just divide this by 100 and you'll get 0.01 as a strain value. So yes, we'll just do this, and I'm getting the answer to be 2.4 10 to the power 10. 2.4 10 to the power 10. It says that draw a cross on the limit of proportionality. I've already done that. It says that state the condition necessary for an object to be in equilibrium. That's pretty self-explanatory. You just need to know that For an object to be in equilibrium, the resultant force on it is 0, meaning the sum of upward force, downward force, left, right, in any direction must be 0. The sum of it, there must be no resultant external force acting on the object, as well as there should be no moment in any direction due to the pivot. So it could be in the clockwise direction, could be in anti-clockwise direction, that should be 0. So that's just it. You can write it however you want, but that's pretty self-explanatory. We'll move on. So I already solved this, so let's go. It says a wire is used to hold a uniform shelf horizontally in equilibrium. I'll just highlight this, that it says it is equilibrium. The wire is connected to the midpoint. Okay, this is the midpoint, and it sells a uniform shell. Uniform shell means that basically if you know the entire length, you're able to dissect it in other like ratios. Like it says the wire is connected to the midpoint, you can take 0.65 and divide it by 2, and you know what this length is. Okay, but we're not going to do that right now. We'll just read the question completely and let's see. Sorry about that. It says the wire is connected to the midpoint of the shelf AB at an angle 50 degree, okay, to the horizontal. The shelf is attached to the wall by a hinge at A. Yes, it is attached to a wall by a hinge at A. And okay, what else? The length of the shelf is 0.65 meter and its weight is 33 Newton. Okay, so its own weight is 33 Newton. A cup of weight 15 Newton rests on the shelf with its center of gravity at a horizontal distance 0.12 meter from B. Okay, because they have told us that this is an equilibrium, you can say that the sum of anti-clockwise moment, anti-clockwise is equal to the sum of clockwise moment. So first we'll look at the anti-clockwise moment. Okay, so if this is clockwise, then this should be anti-clockwise. This should be anti-clockwise. So we'll see in like, okay, we know that this will cause a clockwise, so this is not anti-clockwise. We know that this weight will cause clockwise, so this means that the weight which is acting anti-clockwise will be due to this tension in the wire. Now there are two ways you can solve it if you're able to find, because moment by definition is the force and the perpendicular distance from the pivot. If you look at here, this is the parallel, this is the perpendicular. If you want to just use T, you need to find this distance, because this distance is perpendicular to T. Or you can do what he has done, you can find the vertical component of the wire, which is, you can easily find this. He did T cos 40, you can also do T sin 50, that will give you the same thing. T sin 50, T cos 40. So this is the anti-clockwise, this will produce in an anti-clockwise direction. Okay, we'll see. So clockwise we have force which is T cos 40, and the perpendicular distance we'll have, since it is from the middle, I know, and this is the uniform rod, I'll do this, the total length divided by 2, and then we'll do anti-clockwise we know that, so 1.5 Newton, and multiply this by 0.65. You can actually find it out with a calculator, I am just doing it a much faster way, minus 0.12 meter. Okay, and plus the weight due to the shelf itself. This is very important because it also has a weight itself, 33. I'm getting the clockwise moment to about 11.52, and then I'll divide this by 0.65 divided by 2, and after, so I'm left with T cos theta, and I need to find the value of T. I know that the theta is 40, so after finding out this, I will further divide it by cos 40.
0.3, 0.325.
So I'm getting the value of t because if it's going there, I will cancel the t and it's being divided there. I'm getting the value of t to be 46 point, let's see, 46.352. So 46.3, because we are given majority of the value in two significant figures, I will round this off to 46. So 46 is the answer. Okay, moving on to the next question. It says the stress in the wire is 1.5 10 to the power 7. Determine the radius of the wire. This is fine. We know that stress is equals to force upon area, and we find, so force always mean tensile or tensile force or compressive force when we're dealing with the chapter of deformation. A lot of people get confused with pressure. Pressure force deals with the normal contact force, and we already have the tensile force, which is 46. So we have 1.5 10 to the power 7, that is equal to 46, and we know that the area of a wire is just pi r square. So that is equal to pi, sorry, not that, that is equal to pi r square. If we rearrange the formula, it will give us pi into r square into 46 divided by 1.5 10 to the power 7. Okay, now we know that if pi is being multiplied here, it can be divided there, so we'll cancel that out. And we know that r is squared here, and we just want the radius, which is just r, so we'll under root it. So the r square and the under root cancels out, but there will also be an under root here. So I'm getting my answer to be 9.9 10 to the power minus 4. So that's 9.9 10 to the power minus 4. This is after rounding off, so you might have to round off. How do we know this? We know it's saying that the stress is double. So we know stress is 1.5 here. So doubling it will give us 3 10 to the power 7. But if you look at the graph here, here is the limit of proportionality. Here it is, here's 24. So even after doubling it, even after getting 10 to the power 3 to the power 3 10 to the power 7, our limit of proportionality is still 24 10 to the power 7. So even after doubling, we will still be in the limit of proportionality, meaning Hooke's law is still obeyed. Meaning when the force is removed, the object will return back to its original position. So you can say that number one, the the wire will act elastically. Number one, don't write it in bullets point, I'm just doing it because it's more convenient. Elastically, as even after doubling the stress, it's better if you write the value stress of stress comma 3.10 cent. It is still less than the limit of proportionality which is 24 10 to the power 7. So it's just a very easy question. The wire will act elastically, as even after doubling the stress, which is 3 10 to the power 7, it is still less than the limit of proportionality, which is 24 10 to the power 7. Yes, if it had passed beyond the limit of proportionality, then it would have not act elastically, as after that there would have been permanent deformation and the object would have not returned to its original position. On to question number 4, it says, with reference to the direction of transfer of wave, compare the oscillation of transverse wave with longitudinal wave. This is again a very simple question. So if this is your transverse wave, this is the direction of where your energy is being transferred. This is energy. But if you look at your particle here, This is moving either up or it is, yeah, this is moving either up or it is moving down. So the movement of the oscillation of particle is perpendicular to the direction to the transfer of energy. However, if you look at a sound wave, which is like you have rare compression and then you have rarefaction and then you have compression and then you have rarefaction, so you see that like there is compression, then there is rarefaction, then there is compression, and then there is rarefaction. So all particles are oscillating in this direction, left right left right left right, but your energy is also being transferred in this direction, like in so basically in longitudinal wave the oscillation of particle is parallel to the direction of the transfer of energy, but in transverse wave, because our particle are moving up and downward, while our energy is transferred either to the left or either to the right, is perpendicular. Okay, it says a pipe is the pipe is okay. मेरा गला दब मैं ज़रा पानी पी के आ रहा हूँ. Okay, it's written that a pipe is open at one end and closed at the other. So this is the classic example of stationary wave, the one open and one closed pipe. The piston can slide freely at a distance. The piston can slide freely and is at a distance of 4.5 10 to the power minus 2 meter from the open end of the pipe. A loudspeaker is positioned near the pipe and emits a sound wave of single constant frequency. Okay, kya raha hai on figure 4.1, draw light array on the position of antinode. I've already done that. Then it's saying that the speed of sound in air is 340 meter per second. Determine the frequency of the sound. So we know that speed is equals to wavelength into frequency. Now the problem is that we don't actually have the wavelength. What we have here is something that you would perhaps call a quarter wavelength, because a complete wavelength, if you look at here, let me just extend it a bit more further. A complete wave would be something like this. So what you have here, this is not like exactly to proportional. If it was proportional, I think it would be something like this. So what we have here is something perhaps a quarter wavelength. So we have 1/4 of a wavelength and we are told the length of 1/4. So wavelength upon 4, that is 4.5 10 to the power 2. So this is simple math. You can like the 0.25 lambda is equals to this 4.5 10 to the power 2. What will 1 lambda be equal? So you just cross multiply it and you find the value of x, which is coming out to be what was that? Which is coming out to be 4.5 10 to the power minus 2. Okay, that's quarter, and divide this by 0.25, so you get 18. 0.18 meter is the length of the one wavelength. So if you want to find frequency, f is equals to v upon lambda, where this is 340 and you're getting it 0.18. So f comes out to be, let's just calculate it. So f comes out to be 340 divided by 0.1, so it comes out to be 18,188. But because everything is given to us, if you look at here, two significant figure. What else? Yeah, that's it. Since everything is given to us in two significant figure, we'll round it off to 19. Okay, moving on, it says that the piston is moved to the left. Okay, and the frequency of the sound emitted by the loudspeaker is then changed, so that the stationary waveform is formed with the same number of antennae. Okay, so it's saying the frequency is changed. Okay, piston is moved to the left, so piston is moved to the left, So if I'm not very good at drawings, but let me just try to draw something. So it's something like this, and previously it was something like this. Okay, but now what is happening, it is saying that the piston is moving, it is moving much more further to the left. So what should have happened is that because it is moving much more further to the left, so let's say can I choose a more darker color perhaps? I don't know why it's not working. I think I'll stick with red because it is like moving much more further. So you see there's a difference between them. So because it is moving much more further to the left, so it initially the wave should be much greater. The distance covered by the wavelength should be much greater. Okay, but says the frequency is changed so that the stationary frame is formed with the same number of antinodes. So what it means is that because it says that the stationary frame formed with the same number of antinodes. So initially what should have happened is that as it moved more to the left, meaning there was more area, and if the frequency didn't change, perhaps there might have been what? There might have been more antinode, or basically the wave is covering a greater distance, meaning it is covering a greater wave, no, not a greater wavelength, but it's covering a greater distance. So there's also the possibility that maybe perhaps by providing us with a greater distance, there could have been more antinodes formed. You see, it has moved to the left, but there is now one antinode here and one antinode here. But it is saying that the number of antinode forms remains the same at the same time while the length is increasing. This means that our wavelength is changing. Our wavelength is changing. This means that at a greater distance, that at this distance, by increasing the distance, it means that even by increasing the distance, the stationary waves form the wave profile that of a quarter wavelength. But how is this possible? Well, this is only possible if our wavelength is increasing. So if our wavelength will increase, this means that previously if a quarter wavelength was formed at this distance, now it will be formed at a greater distance. So if we want the lambda to increase, so we know that lambda is inversely proportional to frequency. So if this increases, this decreases. So we can explain. So we know the wavelength is increasing. We said the frequency will decrease. Again, please write it in full form. I'm just writing in bullet point. Why? Because the wavelength increases, and as they both are inversely proportional. Define electric potential energy. Potential difference is just a fancier way of saying voltage. That's all that is. And we know the definition of voltage is it is the work done. It is the work done per unit charge. Work done per unit charge. And since it is of 1 mark, you will easily get the mark. But if this was of 2 marks, you will say that in converting electrical energy into other forms of energy, Now you may ask, well, oh my god, that's the most worst looking Y I've ever drawn in a while. Okay, now you may ask, how or why is that? Well, if you look at potential difference literally mean when there is a difference of potential. Potential means you know what, like as think of potential as a quantity. Think of potential as a quantity of charge. If there are two, if there is a wire, let me just draw a wire. If there is a wire here, and this region has a like more positive charge, it is more positively charged, and this region is also positively charged, but the magnitude of charge here is greater and the magnitude of charge here is lesser. So there is a difference of potential from one point to another. So voltage is just the flow of current, and sorry, it's just the flow of charges from a higher potential to a lower potential. Since it has a greater potential, it has a lower potential, the charges will flow in this direction. That's all potential difference is. Current is the flow of charges, and potential difference is the flow of charges from a region of higher potential to a region of lower potential. So that's all that is. You may ask na kabhi, if you might think of it sometime, why is that, like if you have a circuit, like this, and there's a component here, why is that the current, like the charge is flowing at all? Why doesn't it just stay here? Well, it is because that if a charge is here, it's positive, this region is positive and this region is negative, so it will go from the positive region to the negative region because it is moving from a region of higher potential to a region of lower potential. That's why the charge is moving. Okay, we'll actually move on to the question. Okay, it says that a power supply, 3 resistors and a variable component X are connected in the circuit. Okay, let's look at the circuit. There is a power supply and there is an 7 amp current. 2 resistors, sorry, 1 2 3 4. There are 4 resistors and they are 3 of them are connected in parallel and one is here. Okay, what is it asking? The power supply has an electromotive force of 230 volts and negligible internal resistance. The current in the power supply is 7 amp. Identify component X. Component X is actually a heater. So there is no explanation here. This is just, I'll put a link in the description to, like, if you look in your own physics book, there is a page in which they have identify all of the electrical components. So it's a good practice if you memorize them before your exam. Okay, it's saying it showed that the potential difference across the resistance 0.86 and 0.866 voltage. Easy, you'll just use V is equals to IR and you need to find V, so you'll take I think 7 and 0.86. I'm getting V to be 6.02, round that off to 6 and you get your answer. Then it is saying calculate current I. Okay, so one thing that I can see, and a lot of people makes the mistake that a lot of people make here is it's saying current. Now you know what they think. They know the formula of Kirchhoff's first law, that the sum of current entering a junction is sum of current exiting a junction is. That's true, but and they okay, that's true. So because this region was in series, so current remains the same in series. So the current across this component is 7 ampere. Then it is spreading here. Okay, now but we need to know how much current is spreading here, because in parallel the current divides. So let's look at it. We know the voltage in parallel remains the same. So if we are able to, we know that its resistance 170 ohms resistance, so we can essentially find the current I, because we know that this is 170 and we know the voltage across it. So let's find I. First we'll find I2. So I'll say I2 is equals to V upon R. V is 230, R is 170, cancel out the 0, so 23 divided by 7, 17. So I'm getting the answer to be 1.352. Okay, you can round this off, but I don't like to round this off. I want to see till the end. Okay, Okay, then it is saying we know that this, so now it's relatively simple because we know according to Kirchhoff's first law the total current entering a junction is equal to the total current outgoing a junction. Sorry, it's not this. Plus I2. So this is 7 minus 1.35, and I will get I1. Let's see what that is. 7 minus 1.352. So I'm getting I1 I'm getting 5.65. I'll round this off to two significant figures, so I'm getting 5.7 amps. Hopefully I made that clear. Let's move on to the next question. Okay, moving on, it is now saying that calculate potential difference across component X, meaning the potential difference across X. Now, one mistake that people make, yes, it is true that when dividing in parallel, the current remains the same. But if you look at these two components, they are not connected to one another in a parallel combination. They're actually in series. So what that means basically is that there will be some of the voltage that will be used here, and then after being used here the remaining voltage that we'll have will be actually here. So first we need to identify what is the voltage that is actually being used here. So we know I1 we calculated, and we know the resistance, so we can find that out. So we are finding the voltage used across the resistor of 2.4 amperes. So I have 5.7 and multiply that by 2.6. I'm pretty sure that's the resistance. Sorry, 2.4. 2.4. 5.7. Why isn't it working? Okay, moving on to part 3. It says calculate the current I. Now the current I, if you look at here, according to Kirchhoff's first law, the sum of current entering a junction is equal to sum of current outgoing a junction. So here 7 across this component, it will also be 7 because this is series, and current in series remains the same, but it will be divided differently here. But if we look at these two places, we know that the voltage remains the same in parallel. But you know, there's a big mistake that I've seen people make, is that what they do is that they think the current going here is 230 and the current going here is 230, but they disregard that some of the voltage has been utilized here. So it will not be 230. If you do that, you don't get marks. This will actually be 230 minus the voltage that we use here, which is 6 volts. So it's, do show this in your working. So it will be 230 minus the voltage that has been used across the resistor of 0.86. So you'll get 224. Now this is the voltage that is going in I1 and I2. But in order to find I1, we first need to find I2 because it's much more simpler. Why? Because we already know the resistance and we know that the voltage across it will be 224. So using simply V is equals to IR, using I2 is equals to V upon R, which is equal to 224 divided by 170. Let's see what you're getting. So it will be 224 divided by 170. I'm getting 1.317. I'll round it off to two significant figures, so I'm getting 1.3. We know that I total is equals to I1 plus I2, and this is 7, and I2 is being plus here, it will go there and it will get minus 1.3. We get I1, and I1 is equals to 5.7 ampere. So we write 5.7. Now it is saying calculate the potential difference across component X. We'll look at here. Now across component X is the same phenomena. If you look at here, 2.4 volts and X are connected in series. They are not connected in parallel. So this means that of the 224 voltage that comes here, first there will be some voltage that will be used here, and after the voltage that has been used here, we will have a voltage here, let's say 224 minus the voltage that has been used by the 2.4 resistor. So first we'll find the voltage that has been used by 2.4. So we'll use again V is equals to IR, and we need to find the voltage across it. So we know that the current across it is 5.7 multiplied by 2.4. Let's see, I think I got something like, for this I got 13.68. So we'll round that off to 14. So, and to find the current across this, so we had 224 voltage, the total voltage, minus that by 14, and we are getting 210, and this is your answer, 210 voltage across the component X. It now says calculate the power dissipated by component X. So it's only asking the power used by component X. So you can use whatever formula you would like. Let's see what is given to us. We know the resistance. Yes, we know the resistance. We know the voltage across it. Yes, we even know the current across it. So we also know that. So you could use like all of these formula. All of these are valid. If you use like P is equals to IR, that's correct. P is equals, sorry, if you use P is equals to, why am I writing R? P is equals to I square into R, or even P is equals to V square R. All of them are correct. I'll use the simplest. P is equals to IR, so I'll just use P. Do I know the current across it? Well, yes, the current remains the same. And do I know the voltage across it? Yes, I know the voltage as well. So let's see, 5.7 into, we know the voltage, so it gives me 1197. Round this off, you'll get 1200 watts. 1200 watts. The purpose of the circuit is to provide power to component X. Determine the percentage efficiency of the circuit. So, a second. This is asking for, this is saying the purpose of the circuit is to provide power to X. Yes, I'm told that. But it's also saying determine the percentage affinity of the circuit. Oh, so we are taking, okay, we are only taking this into regard by taking, so first I'll find the total power, which is P out. This is the formula for percentage affinity, input into 100. What is P in? The P input. Well, what is happening? So I know the input power, the total current is 7, and 230, the total voltage that was given to me. So 7 into 230, that I'm getting 1610. And it's saying provide to power component X, so it should be 1200 upon 1610, cancel the 0, 120 divided by 161 multiplied by 100. So I'm getting 74.5. Round this off to two significant figure, I'm getting 75. Okay, I can easily get this. The resistor of resistance 170 ohms is removed, leaving an open circuit with the lower branch of the circuit. There is no, wait, leaving an open circuit, okay. open circuit. There is no change in the resistance component of X. Okay. So wait, so it's saying that this resistor is removed, but at the same time, when this is removed, it would mean that there is an open circuit, meaning there is nothing connecting them together, meaning all the voltage and all the current will just flow through this, and no current will flow through this, because the circuit is now open. So we know that whenever resistors are in parallel, their combined resistance will always be low, the total resistance will always be low. And as this resistor is removed, meaning these two resistors are now in a series combination along with this resistor. So this would mean that the total resistance is actually increasing. Mean that whether it would mean that the current in the power supply is decreasing. Okay, now it says compare an alpha particle with a beta particle in terms of their masses and charges. Okay, so let's see what this question is worth of. This question is worth of 3 marks. So let's see. First, it's better if you don't do it like this. I'm just doing it for the sake of time. But the mass of an alpha particle, if you look at here, it has 2. It has a +2 charge, but it has 2 proton and 2 neutrons, 2n, 2p. So it has a total charge of 4u. What is u? U is a constant. This is a value that you need to know. This is basically the mass of one proton, which is 1.66 10 to the power minus 27. This is the mass of one proton, and also this is the mass of both proton and neutron. So this is just an alpha particle has a charge of 4u, or you could say 4 into 1.6. एक second. हाँ. So it has a mass of 4 in u, or 4 into 1.66 10 to the power minus 27. You don't need to show this much detail, but this is okay. If it's better if you do it. As for a beta or a beta positive, beta positive is actually has the mass of an electron. So both beta negative and beta positive has a mass of an electron. So, and the mass of an electron has a mass of 1/18 u. This is important that you refer the u. A lot of people say 1/18. 1/18 what? Apples and bananas. 1/18 u. You can write 1/18. You could write 1/1836, or even 1/40, because all of these values are accepted. The actual value of an electron, the mass of an electron, is 1/1836 u. That's the actual mass of an electron. But 1/18 is the most repeated valid answer that I've seen in the marking scheme, but all three of their answer is accepted. Now it's saying that mass and charge. Alpha particle has a charge of +2. Don't write electron. +2, just write +2. While it's saying that it's a beta positive. We know in a beta negative particle and neutron is converted into a proton. So the charge is increasing, and in order to balance that out, we have a beta negative particle. Beta negative particle has the charge of an electron, because if you look at the definition of radioactivity, a lot of things in it remains conserved, like the work remains conserved, the momentum remains conserved, the energy remains conserved, but the charge also remains conserved. So since all of these values are remaining conserved, the charge of the beta particle that has been emitted will also be opposite to what the conversion has taken place. For example, For example, in a beta positive, I think a proton is converted in a neutron. So what is actually happening? Since a proton is being converted into a neutron, so there is a decrease in +1 charge due to a decrease in proton. So in order to balance this, beta positive will have a charge of +1, so that it balances that out. So you would say that beta positive has a charge, it has a charge, have a charge of +1. I don't know why I keep writing and it has a charge of -1. This beta plus particle is a positron and has a charge of, positron is just the opposite of an electron, of +1. Then you will just write that then you will just compare the value. You can say alpha particle has a greater charge than a beta positive particle, and that it has a greater mass because it is much more heavier than beta positive particle. Okay, moving on. It says that nucleus P undergoes alpha decay to form nucleus Q. Nucleus Q then undergo further decay to form nucleus R. So this is nucleus P. It undergoes alpha decay. So this is the nucleon number. It should decrease by 4. It should decrease by 4. So 1, 2, 3, 4. Okay, to form nucleus Q. And also the proton number should also decrease by 2. 1, 2. So the 1, 2, 3, 4. So it should have been somewhere here. And then it says that nucleus Q then undergo further decay to form nucleus R. So if you look at here, the nucleon number remains the same, but there is an increase in a proton number. So this is a clear indication that beta minus decay has taken place, because in beta decay, beta minus, a neutron is converted into a proton, but the mass remains the same. It says that draw a cross on the proton and nucleon number of Q. I've done that. State the name of the particles emitted as Q decays to form R. So we know that beta negative is taking place. So something like this should be happening, that we had Q 212, it has a proton of 82, it undergo beta negative decay to form R, which has 212, it form 83 plus beta negative and electron antineutrino. So you could say this is self-explanatory. Antineutrino or electron antineutrino both works, and beta negative particle. You could also write beta particle, and you can also write an electron, because beta particle has the charge of an electron. Both are accepted in the marking scheme. Before the decay, P is traveling at a constant velocity, okay, and after the decay, Q has a velocity of 1.3 10 to the power 5 at an angle 68 degrees to the original path P. Alpha particle has a velocity of 150 10 to the power 5 meter per second. That's a huge velocity, and at an angle theta to the original path. So this is again a recurring type of question that I've seen a lot in dynamics. So we'll just use, because it is saying it's traveling in constant velocity, I know that the momentum remains conservative, and says use the principle of conservation of momentum. So before decay or before collision, it had a momentum of, it was traveling with a constant velocity. But I don't know what is momentum in the x-axis, but I know that in y-axis, which is this, the vertical, this is x and this is y. Because it is traveling in this direction in the horizontal plane, I know that its momentum in the vertical plane is 0. So in y-axis, its momentum before collision was 0. So before decay, if it was 0, meaning after decay it must also be 0. We can obviously see that some of one alpha particle is moving upward while nucleus Q is moving downward. This means when you take the value of this and takes the value of this and add them together, you'll get 0. So we'll see. So let's just write this down. I know that in alpha particle, I'm first taking alpha particle is 4u into what? Into 150 10 to the power 5 sine, because it is moving in the upward direction, sine theta. Now I will choose minus. Why minus? Because this is a vector quantity, and if I'm taking the upward direction as positive, I will be taking the downward direction as negative. So the downward will be negative, or you could even do this plus. Since it is undergoing decay and nucleus P had a mass of 216, we know it's going to be 212 u into 1.3 10 to the power 5 sine. It's not sine theta. I think they have told us the angle, that's 68. So this is going to be 68. So in the end, I'm just briefing over it. Sine, this will remain here, this value will go there, this is right now negative, it will become positive. So sine theta is equal to the downward vertical momentum of Q, so it will be 212 u into 1.3 10 to the power 5 sine 68, and divide this by 4u 1.150 10 to the power 5. The u and u will cancel out. You will divide these together, and what you will do, you will get an answer for this ratio, and afterwards you will do sine inverse. You will take the answer and you'll find the answer. So I'm getting sine inverse 0.4257, and if you plug that into the calculator, I'm getting 25 theta. Energy of the alpha particle, we know that kinetic energy is equals to half mv square. Please do write this formula. Majority of them I've seen in marking scheme that they avoid. Even if you have the right answer but you didn't wrote this, you will not get the full mark. So write the formula beforehand. So it's going to be half into 4 into 1.66 10 to the power minus 27 into 150 10 to the power 5 square. I'm getting my answer to be 7.5 10 to the power minus 13. So 7.5 10 to the power minus 13. If you have any query